Polluted water is passed through a series of filters. Each filter removes 90% of the remaining impurities from the water. If you have 10 million particles of pollutant per gallon originally, how many filters would the water need to be passed through to reduce the pollutant to 500 particles per gallon? All right, so this is kind of an interesting question. It is an exponential decay question because we have a percent. So let's just kind of get a feel for what's happening here. So we're starting with 10 million particles. All right, and they're going to go through some kind of a filter. And that filter is going to remove 90% of the impurities from the water, which means, so these are the impurities. These 10 million particles are, they're the pollutants. These are the impurities that we're trying to remove. So it's going to remove 90% of them, which means we're only going to have 10% of the impurities left. It's going to remove 90%, so we're only going to have 10% left. All right, then those particles are going to go through some other filter and remove 90% of the remaining impurities. So that means after 2 filters, this is the number of particles that are left. 10 million times 0.1 to the second power. All right, so if we say the number of particles left after n filters is going to be the number of particles that we start with times 0.1 to the n. So this is a very common exponential model. The difference here compared to some of our other models is that n is not a time period. It's the number of filters that it's going to pass through. All right, so we want to figure out how many filters it's going to have to go through until we only have 500 particles per gallon left. So we are solving for n. We are solving for the number of filters. Now, sometimes when we're putting in 10 million, a number like 10 million, we change it to 10 and say that the output's going to be in millions. All right, so we say number of filters, particles. So do I want this P sub n to be in millions? Well, remember, we're going to try to figure out the number of filters is required to get this down to 500. If I write this P sub n in millions, I'm going to have to change 500 into some number of millions, which is kind of awkward. Like it's way less than 500,000, you know, trying to figure that out might be difficult. So in this case, because of the 500, I'm going to say we're not going to do this in millions. We're going to write out all the zeros. So our P sub 0 value is 10 million. Instead of writing 10, we're going to write all of these because, like I said, what we want to do is figure out the n so that the P sub n is 500. So I want to leave this as 500. Okay, so we're going to go ahead and use Desmos. We're going to go to Desmos and we're going to type in y equals 10 million times 0.1 to the x. And then we're going to type in y equals 500, which is going to be that horizontal line, and see where these two things intersect. Now this is an interesting example to do with Desmos because the numbers are so big. Getting the scale right and getting the graph to look good can be a little challenging. So I want to show you how to do that. So first thing we'll do is put in our equation y equals 10, 123 million times 0.1 to the x. Now I could kind of see what's happening over here a little bit, but there's a lot of stuff I can't see. And then we're going to type in y equals 500 to see where they intersect. Now this isn't even up at 500, right? Now if I wanted to see this whole graph, I'd have to go all the way up to 10 million. I've talked before about hitting shift and then pulling this down. It's a long way to 10 million. So I think in this case I would use the wrench and I'd set my y. Let's see what's happening up there. I'm going to go all the way up to 10 million. You ready? Here we go. 10, 1, 2, 3, 1, 2, 3. There's 10 million. And let's just close that and see what it looks like. Okay. So there's my graph of the number of pollutants after a certain number of filters. So this is 1 filter, 2 filters, 3 filters. Okay, and I'm looking for 500. My line 500 is here in purple. Now it's so small compared to 10 million that it looks like it's laying on the x-axis, but it's really not. Okay, so that gives me a good picture. Now what I want to do is really see where this green and purple intersect. So I'm going to take this y not to 10 million anymore. Let's get rid of that. We want to know around 500. Let's go to 1,000 and see what that looks like. Okay, let me hit this again. Oh, we got to change this negative. Okay, we're going to change that from 0 to 1,000. There we go. Okay, now I can kind of see, here's the 500. Here's my exponential decay. I can go ahead and click on the intersection point, and it looks like about 4.3 filters before it gets down to 500. Now, there's no such thing as 0.3 filters. So at 4 filters, we could kind of go up here, maybe about right here. At 4 filters, there were 1,000 particles. So to get it to be less than 1,000, it's going to have to go through that 5th filter, which will actually take it all the way down to right around 100. Okay, so let's go back over here. Our actual n value is 4.3. Let's write that down. So to solve this, we're getting n equals 4.3, but in reality, in the context, it's going to have to go through 5 filters. We don't round this down, right? Because if we were rounded down to 4 filters, it wouldn't be at 500 particles per gallon yet. It would be higher than that. All right, so I hope this example was helpful, a little bit different than some of the examples we've done. And an interesting application of exponential decay.